before we start the next worked example, I just want to go through a few important things about vectors. Now we're moving into 3 dimensions. The first thing is for parallel vectors. So if you had a vector u given by -2, 3, and you had a vector v given in the column as -6, 9, what you'll notice is that this vector here times by 3 gives you this vector v. So that means if we were to write it, that v is equal to 3 times u. And in terms of what that means for these vectors, it means first of all that one of these v is 3 times as big as u, but it also means that these vectors are parallel. So the vectors are parallel because they're both going in the same direction. The next thing that I wanted to look at is vectors in 3 dimensions. Okay, so for vectors in 3 dimensions, we've been using x, y so far for 2 dimensions. 3 dimensions, all we do is we just add another column, another row in our column. So instead of being a equals xy, you've now got the point or the vector a, and it would be given by x, y, and z. We call z that third direction. You can think of it as being up. So you've got a sort of a plane formed by x and y, and then you've got another vector coming up out of the plane. We actually say this vector would be normal to the plane. Normal means it's perpendicular to the plane. Okay. Another thing, once we start getting into 3-dimensional vectors, is that you want to look at these useful vector rules. We've already looked at this one. This was that the addition of vectors doesn't matter what order it happens in. When we're talking about order not mattering, that's called commutative. Commutative means that you can just have it either order, it's the same. Multiplication is a commutative operation, for example, just with numbers. Okay. The other identities here, or the other rules that are useful to know, a plus the 0 vector is just a. That's what a 0 vector does. Opposites, a minus a is the 0 vector. Remember the vector, it's not 0, it's the vector 0 whenever you're dealing with vectors. Unless you were wanting to multiply a vector by a scalar, which was 0, but in any other circumstance it's the 0 vector. For addition, you can see the brackets, it doesn't make a difference here what order you add them in. And we also have what's called the distributive law. It's called distributive because you distribute that scalar to both the things in the bracket. So it's just a normal expansion. Okay. The last one is the one we just discussed here. A vector A is parallel to a vector B if there exists a real number such that A equals KB. Okay, so B times some scalar is A. So if we look at the worked example now, we've got this guy here. It's a little rectangular prism, okay, or a cuboid. We've got a few bits of information given to us. The first thing is that O to A is given by A, O to G is given by G, and O to C is given by C. Now I'm actually going to draw those in. I'll do them different colours. So I'm going to do O to A is going to be red. So O to A you can see, and I'll do that as an arrow. There's O to A. Now can you see any other lengths here that I could describe by the same vector, O to A? Well, hopefully you saw that is the same length, same direction, same length, same direction, same length, same direction. So all the red lines there are going to be my vector A. Okay, I'll put that there so we can remember. That's the vector A. The next one, we'll do this in green, is going to be O to G. Oops. O to G is given by the vector G, and we'll do that again with arrows. So you can see O to G. Any other vectors like that? Hopefully you can see C to F, B to E, and A to D. They're all the same direction, same distance. And the last one, we'll just do blue, is going to be OC, which was a good TV show in the old days. OC is this vector going from O to C. Okay, and now again, if we look at any other vectors, you can see this one, and this one, and this one. They're all going in the same direction, they're all parallel, and they're all the same distance or same length because we know that property of this rectangular prism. So now we can actually do the question part. We've got, first of all, we've got A, and that's O to B. Now the question's asking us, find the following vectors in terms of A, G, and C, which we know. So O to B, what we have to do is look at our picture here, and you can see O to B, and I'm just going to draw this as a blue line, is this vector here. Okay, so O to B, we can see we'd be travelling along this blue vector. Remember that the blue vector is C, so we'd be travelling along C, then we'd travel along B, this red vector here, which was A. So it'd be C plus A. Easy. We've answered that in terms of C, G, and A. There's no G involved because we didn't go up. The next one is B. So this might be a time where you want to stop the video and finish these off without me and then just skip to the end of the video and see if you got the right answers for it. Next one is O to F. So again, we've got, I'll just get rid of this one. We've got a vector going from O to F. Having a look at constructing it, you can see we'd have to go along OC, which is the blue one, and we're going in the correct direction. We always add head to tail, and then go up CF, so that's G. C plus G. Next one, C, is G to D. So again, we'll construct that one. C to G is there. This one's a little bit different because you can see now that one of these vectors is not aligned properly. Remember, to add vectors, they always have to be aligned head to tail to add them. So we're going to have to turn one of these vectors around, and it's that blue vector. To turn a vector around, remember that if this is a particular vector, let's call it D, negative D is just the same length but going the opposite way. So we can just look at this vector, the blue vector, which is C. We'd have to go backwards along it, so it would be negative C. But we can go the right way along O to G, which is G. So that would be C backwards and then up. That one's already aligned the right way. D, G to B. Again, just doing an arrow, G to B. Now this one's three-dimensional. You have to think about this in a three-dimensional way. There are lots of ways that you could get here from this point to this point, by the way. You could travel along here, you could travel along here, along here, along here. Try and pick a direction where all of the vectors, or as many of the vectors as you can, are actually pointing the right way. Then you won't have to do so many subtractions. So I'm actually going to travel along this way, and then that way, and then that way to get there. So I'm going to travel along a blue vector, so this is G to B. A blue vector is C. Along the red one, it's aligned the right way, so that's plus A. And then I can see here I'm going to have to go down against the green vector, so that would be a minus G. If you go a different direction, say you went this way, you'd still have A, you'd be going along C, and then you'd be going backwards along G. So you can see it doesn't make a difference which way you get there. You're going to end up with the same final answer there for that particular position vector. Okay, the last one, I'll just erase those bits. And it's a great idea in your notes actually, if you're doing this, trace that particular path that you took when you go in 3 dimensions, even in 2 dimensions, just so you can see what's going on. The last one is from F to A, which is there, F to A, so going across that way. And again, the same thing, pick a way to get there. I'm going to go, there's not really a good way of getting there. There's a lot of things that will have to be backwards. I'm just going to go this way, down, across, and up that way. So for the last one, F to A, you can see I'm going to go down against the green vector, which was G, so backwards along G, the right way along A, and then backwards along C. So it's a really nice idea, with vectors. Have some coloured pencils. There's no reason you can't have coloured pencils or pens or highlighters. So you can actually, on a diagram, show which vectors are the same. That makes it very quick and easy for you to navigate your way around the shape rather than having to label all the vectors. So, and again with this, if you'd chosen to go another way, maybe that way, okay, you'd have negative C, which we have here, plus A, which we have, and then down against G again. So whichever way you go, you'll still end up with the same answer. So that's the way to do a proof, or to actually show vectors in terms of other vectors, identify which vectors are the same, and then work with those.